In these last few vodcasts for Chapter 17, Additional Aspects of Aqueous Equilibria, we'll be looking at the equilibrium of solubility. Now before you start, you're going to need your lecture PowerPoint notes, of course. And I have provided space in your PowerPoint for sample exercises that we'll be covering. However, if you can locate the handout that says Solubility and Ksp problems, you'll find I give you a little bit more space to write down sample exercises 17.11 through 13. So in addition to your PowerPoint notes and various practice worksheets, I've identified a number of worksheets that will be graded for accuracy. So when you get done with this first podcast, I'll explain what you should be able to do at that point in time, and then you will be able to do more higher level problems with the second podcast. So go find Solubility and Ksp problems, go find your PowerPoint notes. It helps if you have a calculator, and we're going to cover the first three sample exercises, 17.9 through 11. So what you see here is an expression for the dissolution of what we call a sparingly soluble salt, barium sulfate, in water. And it only makes a tiny amount of ions, and so it's also reversible, because as these ions form, they can also collide with each other and return back to the solid form. So you would see this in a saturated solution. Some solid will be present at the bottom, and we can calculate a new kissing cousin of the KEQ. It's called the Ksp. And to write a Ksp expression is very simple because we always have a very slightly soluble salt on the left-hand side, and you know solids are drop from equilibrium expressions. That's because their concentration doesn't change because they're a solid, and relative to the minute concentrations of barium and sulfate, it's incredibly huge. So you get to ignore it. So we now can calculate something called the Ksp, which is simply, in this case, the concentration of barium times sulfate ions. These brackets indicate molar concentrations, but as you see, you might be asked to convert into different units of solubility. So what's Ksp stand for? It's the solubility product constant. The bigger the number, the more soluble a salt is. The smaller the number, the less. But they're like weak acids and weak bases. They're not highly soluble at all. They're sparingly soluble, and we can rank the solubility of ionic substances that are sort of soluble by looking at their Ksp numbers. Now, I should warn you, I'm doing this podcast in the presence of two cats. It's possible they might make an appearance, so if you see a black or an orange tabby cat go by, it's cats looking for attention. Today they're thing one and thing two, trapped inside the house on a rainy day. Let me pause this podcast so I can go catch thing one. So I got thing one out of the Easter candy baskets. I don't know, he's a crazy cat. All right, so it's important to know that Ksp is not the same as solubility. Solubility means how much stuff dissolves per unit of volume. Now, as you saw, we can express that in molarity, but a lot of solubilities are expressed in grams per liter or grams per 100 milliliters is a very common one, and you can convert from one back into the other. But Ksp is just a unitless number that shows you how soluble a sparingly soluble salt will be, whereas molarity or grams per 100 milliliters is just a unit of mass or moles that can be soluble in a particular unit of volume. Thing one is fooling around behind the computer screen, so if you hear strange sounds, it's not me. Let's do sample exercise 17.9. Super easy. You can put this one in your PowerPoint notes. If you're asked to write a solubility product constant expression for calcium fluoride, the first thing you do is you look up the corresponding Ksp value from an appendix, and then you write a dissociation equation. Here is thing one. Say hi midnight, say bye midnight. Cats. So I take calcium fluoride and I show it splitting up. You get to assume that not written above this arrow was some water, and the solid calcium fluoride turns into calciums and two fluorides. If I were to write the Ksp expression, it's just concentration of calcium times the concentration of fluoride squared. That's where the most common mistakes are made. People forget that coefficients in the dissociation equation become powers in the Ksp expression. And you could set that to equal to 3.9 times 10 to the minus 11. See how tiny these numbers are? That's why we call them sparingly soluble salts. Only a tiny amount will go into solution when you have expressions 10 to the minus 11. Also, now that you know that the Ksp is 3.9 times 10 to the minus 11 at a specific temperature, which is usually 25 degrees, then you can let X stand for the calcium concentration and 2X stand for the fluoride concentration. You can then substitute in X and 2X and solve for actual concentrations. Now, why do we always have to specify the temperature for a Ksp? Because, of course, you know that changing temperature will make some things more soluble. So in these Ksp appendices, they're always going to say at 25 degrees Celsius. Now, there's another sample exercise that shows how to calculate Ksp from solubility. And this time, they tell you some solid silver chromate is added to pure water at 25 degrees Celsius. That's because it has to be expressed because of what I just said. When they say some of the solid remains at the bottom undissolved, that means it's saturated. So now a little bit of silver and a little bit of chromate ions are going to go into solution. All we know is the silver ion concentration is 1.3 times 10 to the minus 4. What you're asked to do is to calculate the Ksp for this compound. They're really pretty simple, but they always start with the dissociation equation. So here is the dissociation equation. Silver chromate will split up into 2 silver ions and a chromate ion. You always write the Ksp expression, and that would be concentration of silver squared times the concentration of the chromate. Now, what do we know? We know that the concentration of the silver ion is 1.3 times 10 to the minus 4. So whatever amount of silver you have, you're going to have half the amount of chromate ions. Notice that they are in a 2 to 1 or 1 to 2. So whatever concentration of silver you have, you must divide by 2 to find the concentration of chromate. That work is being shown right here. Here is the silver ion concentration, literally being divided by 2 or multiplied by 1 over 2 for the molar ratio. And now we have the chromate ion concentration. Now you simply substitute in those two values into the Ksp expression, but don't make the fatal error that I always do. Don't forget to square the silver. So we punch in the value for the silver concentration squared, we substitute in the value for the molar concentration of chromate, and we calculate the Ksp. Pretty small, 1.1 times 10 to the minus 12. So you can go back and forth from Ksp into solubility or solubility into Ksp, but you must always write the balanced equation as well as the Ksp expression. And don't forget the powers and the squaring, and sometimes the cubing, and sometimes the square root, and sometimes the cube root. There's a lot of opportunity for math there. The concepts themselves are pretty straightforward. Now that was sample exercise 10. We have one more to do, and if you feel like putting sample exercise 17.11 in your other handout that said Solubility and Ksp problems, feel free to do so. It's the same exact problem, but there's a little bit more space. This time, you're given a Ksp, and they're asking you to solve for solubility. So, same thing, write the expression. Here is calcium fluoride splitting up into its calcium and 2 fluoride ions. We put in a little ice chart here, but as you get good at these, you may not need to do an ice chart. So what we assume is that we start with none of the salt dissolved, so that's why there's 0 here. And whatever amount of this calcium fluoride dissolves, we'll call X in calcium, and therefore 2X in fluoride, because they have a 1 to 2 stoichiometric relationship. Now I compulsively should have drawn the Ksp expression for that balanced equation as seen here, and now you substitute in X for the calcium and 2X, and don't forget to square it. Now, if you're like me, I see 2x squared, my brain writes, hey, 2x squared. It's 4x squared times x equals 4x cubed, and that should be equal to the value of the Ksp that was supplied to us, or which you locate in an appendix at the back of the book. Solve for x by taking the cube root of 3.9 times 10 to the minus 11 divided by 4, because you had to get rid of the 4 over on the left-hand side. And now you have x equals 2.1 times 10 to the minus 4 molar. Now that's pretty key. If they wanted molar concentrations, you could have stopped there. But if I reread the problem, it says grams per liter. Oh, bummer. So I got a little bit more work to do. You do know, of course, though, that if this is a solution for X, that's the calcium, 2 times this number would be the concentration and molarity for fluoride. So now let's go turn moles into grams. So we've got our molar solubility is 2.1 times 10 to the minus 4. Sometimes they might ask you for the molar solubility for each ion. In this case, they just want to know what's the solubility in grams per liter of the calcium fluoride original compound. So since it's a 1-to-1 ratio between calcium fluoride to calcium, you can assume that the molar solubility of calcium fluoride is 2.1 times 10 to the minus 4. I have to change that from moles to liter into grams per liter, and as you can see, simply multiplying by the molar mass will achieve that problem. And sometimes they throw another level of difficulty at you where they ask you to solve for per 100 milliliters of solution. And so instead of per liter, you'd have to calculate that per 1/10 of a liter. Now at this point in time, you should be able to do many of the practice problems that you can find. And there were a number of worksheets that were given to you on the packet that you got. And you'll find that there's one called Solubility Equilibria. That's for practice. The answers are actually given, and at this point you should be able to do questions number 1 through 4 on the worksheet entitled Solubility Equilibria. You should also now be able to do many of the problems that will be on the worksheets that will eventually be graded. Those include calculations involving solubility products. There's another worksheet that's a multiple choice worksheet, and you will find 2 free response questions, of which you can probably do the starting problems in those. So I would start with solubility equilibrium number 1 through 4 to practice, and then take some time to do a few of these basic problems: how to write a solubility expression, how to go from Ksp into solubility, and vice versa. Until then.